Here we go. So this is the latest chapter in our work on a very unusual compiler for a subset of Haskell. All the people in this room who work on language implementation, maybe with a focus on the runtime system and memory performance, know that data representation is extremely important. It's at least as important as all the work we put into transforming code to make it more efficient. If your compiler uses an inefficient data representation, you're kind of hamstrung from the start. So coming back from ICFP 2016 in Japan, I think, I was just feeling very upset with pointers. Pointers are littering our heap everywhere. And all our language implementations, pretty much without exception, use at their base the kind of simple runtime layouts that Andreas was talking to us about this morning. So they've got structs, they've got arrays, they've got numbers, right? But those structs are always small heap objects, and they're always connected by pointers. So like the picture up at the top here. So this is what I would consider a fully pointer-based representation of something like a tree. It doesn't matter if it's Java, OCaml, Haskell. It's all, there are small differences, like what is the layout of the object? How big is the header on the object, and so on. But overall, the basic idea is the same. And at the other end of this spectrum that I'm picturing here, there's fully serialized representations, the kind that we might write to a disk in a binary format or that we might send over the network when we want to be really efficient with space. So this experiment, this Gibbon compiler that I'm talking about today, is somewhere in the middle here. We try to, as often as possible, use the very dense representation as our de facto heap representation for all algebraic data types that the compiler uses. So there's a lot of magic in the compiler that goes into making that happen in terms of figuring out how to co-locate multiple heap objects together and allow them to be as small as 1 byte. So these individual heap objects here are 1 byte wide. They're essentially just a tag. So this is node, leaf, and so on. But the topic today is about garbage collection in this world. And the reason you need garbage collection is that the whole memory, unlike one of those WebAssembly modules, we can't just have a single flat array as our entire memory. We're compiling a higher order program that we start with, and there are many values in the program, and there are reasons that pointers sneak back in. So even though we bias everything towards serialized, we end up only mostly serialized, and we still need to garbage collect. But our ideal, of course, if we're doing something like a tree traversal, our ideal is to do linear sweeps with nice, predictable memory access patterns over these buffers. And this is true both in allocation and in reading data. So even if you start with a high-level program, like a Haskell program that traverses a tree, what you end up with at runtime, it maintains a single pointer into a buffer that you're allocating into, sweeping from left to right. And then when you read the tree, you're doing the same thing, reading from left to right. So to give a sense of the motivation for this, like why do we go to all this trouble to have a very exotic data representation? It's because if you're processing things like HTML data or program representations inside a compiler, if you're doing tree traversals, this makes a huge difference. And I'm always, microbenchmarks get a bad name, right? We'd rather have our real Android application benchmark suite. But I also feel that microbenchmarks can be very educational. It's interesting to me that you can take a simple program that traverses a tree and get 2 orders of magnitude difference from different compilers with basically the same source code. So this is a plot from our eCoop 2017 paper on this Gibbon system, where we showed that this simple kind of tree traversal, even your kind of your basic C code is going to be 7x slower than what you can get if you use the denser representation. And that's why Gibbon here is leading the pack in this particular shootout of compilers. Things get complicated when you move away from doing these bulk traversals. So bulk traversals are great because I process the whole tree coming in, and I produce a new tree coming out. I transform it into that left to right sweep over a buffer. But we're compiling these arbitrary functional programs. So we have to deal with programs like this one, which takes a tree as input and wraps just one extra node constructor around it, which ends up being either a deep copy, which would be very inefficient. We take a billion node tree, and we want to add a leaf to it. So we copy all billion nodes there and add 1 leaf to the front of it. That's obviously a no-go. It changes the asymptotic complexity of the source program. The programmer would be very unhappy. So we're forced to reintroduce some notion of indirection. We want to do a constant size small allocation. We want to introduce back a pointer that points to this other pre-existing data. So you'll notice there's a little extra tag here. And that's because as we read these byte streams, we expect the default be that all data, all scalars and other data constructors be inlined in the byte stream. So it's kind of the exceptional case. It's like an escape code to say, OK, now we're actually going to have an indirection, and you have to redirect the byte stream somewhere else. So that's what our pointer looks like. And actually, inside our compiler, we do transform the algebraic data type to have an additional constructor for this indirection. So when we're pattern matching on this data type, handling the pointer case is just one more case in our switch statement that deconstructs that data. The first version of Gibbon, like in that 2017 paper, used region-based memory management exclusively. So we hadn't yet gotten to having a garbage collector, which is what the present work is about. So in region-based memory management, for those of you not familiar with it, you have lexically scoped regions into which heap objects are allocated. Famously, the MLKit compiler did this. Our version of region-based memory management is actually a bit of a compromise because we allocate all regular functional data into these regions, but we allow data to escape regions as well. So region X, as in our example where we're adding to a tree, if we add a pointer to an old pre-existing tree, that would be, for example, region Y might point to region X. We actually allow at runtime pointers between regions and regions to keep other regions alive. So regions in our lingo become the chunks that we allocate into. And our first version of memory management in this exotic compiler setting was purely reference counting based. So we would have these chunks of data, which would usually but not always contain multiple heap objects, and they would be reference counted. The pointers between them would be, therefore, be the references that we were counting. So the way we implemented this would be, here's two regions. One has reference count 1, one has reference count 2. We would track the outgoing, we'd actually track the full set of regions that are outgoing from the full set of outgoing pointers, and we'd remember those for various purposes. And we try to maintain this fast path stack style allocation, where if you allocate a bunch of data into regions with let region, and then they are actually free and not escaping, by the end of their scope, you just deallocate them immediately. But if they persist longer, then they'll only be deallocated later when their reference count drops to 0. So this is fine if you don't have that many regions, if you're doing bulk traversals on them, and if your number of heap objects per region is fairly high on average. So that's why when we're doing bulk traversals over tree data, we achieve a 2.3 and a 1.5x geomean speedup over GHC and Java, respectively. But we initially in this project were focused on the strengths and not enough addressing the weaknesses of this approach. So the weaknesses of this approach is, of course, if you write programs that do many tiny small allocations, then we basically are a under-engineered, poor version of a memory system that compares fairly badly with a 7.4 and 3.1 GX geomean slowdown compared to GHC and Java. So the purpose of this paper was to kind of reintroduce and adapt established memory management techniques to be able to claw back some of the benefits for these small allocation programs, not necessarily to exceed there, but to mitigate the weaknesses while keeping the strengths. And there are also some other disadvantages to using this reference counting approach that I mentioned before, and I'll get into those a little bit in a minute. Our kind of poster child for a program that behaves very badly under this purely reference counting region-based regime is reversing a list. So if you, for example, do an insert into a tree, at least you get log in new nodes within the region that you allocate. In this case, you only get a single con cell, worst case, in every region. And the reason for this is if you can imagine, if any of you are familiar with the way region-based allocation works, you've got a cons here, a cons expression that's being passed to the recursion. And when we infer regions and insert let regions in this program inside the compiler, we're going to end up allocating a new region here. And that new region, for every single con cell, will point back to the result of the reverse. You can imagine a sufficiently smart compiler trying to do reverse in place inside one buffer, but it would be very hard. We'd have to have regions that grow from right to left as well as left to right, and you'd have to know exactly the size of the list in advance. Which we don't do. So currently, Gibbon will end up with this fragmented result from a reverse. So if you take an input which is compact and serialized in the way that we like it to be, running reverse on it will give you this memory representation. You'll actually even have this little extra pointer, this little extra header object at the beginning, which isn't great either. And that's kind of because of our destination passing style conventions internally. Anyway, you'll notice in this case, we have a number of disadvantages because now we're wasting extra space on these little indirection tags as well. So we really want to avoid this as much as possible. And you can see here we're 3.5x slower on reversing a list than GHC, 2.75x slower than Java. So our goal for this work is, again, mitigate those weaknesses. And we do that in the tried and true way of introducing a generational collector. And we keep that reference counting system as our old generation. We insert a new copying collector as our young generation. So that basically gives us a lot of the advantages of copying collectors, except they work out in a slightly different way in this region-based environment that I'll show you about. So first, I mentioned it's largely traditional. So this means we're bump allocating into a nursery. The nursery is one big space here. And what we're bump allocating are essentially little mini regions. They could be as big. In some cases, we statically infer their size, and we say this is one con cell. In some cases, they're kind of a minimum size, like maybe they're a kilobyte, and we expect multiple regions, multiple objects to go in them, but we don't know how many. We need a lot of dynamics. We need to handle a lot of things here that are unusual. For example, our objects, if you think of these little regions as objects, they grow. And so you might allocate a small region, allocate some heap objects into it, some individual values, then have it overflow and need to grow in some way. So that complicates things. And so you can see in the paper there are various strategies for eagerly promoting when you need to grow a region and so on. Now, once things get collected to the old generation here and we evacuate, there's a number of beneficial properties to this. But one of them is simply that you of course, get the usual locality benefits from copying, and you eliminate things that have died and all the normal kind of exploiting multimodal lifetimes, as we've always done in generational collectors. But you also get some unique benefits that I'll highlight in a second. But first, let me tell you a little bit about how this GC works. The GC is largely traditional, I mentioned, but evacuating here has a couple of special concerns that you can check out in the paper. One of them is that you want to make sure to sort your root set so that you try to keep the data that's copied to the old generation as much in line as possible. If we reverse that list and then we evacuated it in the wrong order, we'd end up with the same fragmented representation. We want to reverse it. We want to garbage collect the reverse list in a way that it ends up back in a compact in-order form. So the punchline with that reverse microbenchmark would be that you would still within the nursery create the individual con cell allocations. But then if the reverse list lives long enough, it will be evacuated to the old generation. It will be back in a compact form. And you can check the paper for the details of how we sort the root stack. And the upshot of all this is that our new collector has a number of unique benefits here. It's got the old standard benefit of efficient bump allocation in the nursery that everybody would expect. But it's also got this kind of extra strength benefit of compaction. So it's not just the normal locality principle of copy and collection where we put objects close to each other. It's the extra magic benefit that when you put them close to each other in the right order, they get much smaller because the pointers disappear. So that we feel is an extra strong motivation for using this architecture in this exotic scenario. But there's also a number of challenges that we have to overcome in order to adapt these traditional copy and collector and generational collector techniques to this unusual environment. So one is just that we're very cramped. So these objects do not have a full header word. They are not aligned on a word boundary. We in part, this approach is efficient because it's utilizing the efficiency of unaligned access on modern architectures. We have all these 1-byte objects floating around, which means that the 4 and the 8-byte objects are not aligned. We've got sort of a soup of bytes as our representation. And in that world, you don't always have space for a forwarding pointer, which the people in this room are probably familiar that forwarding pointers are often used during garbage collection to remember that you've already relocated something so that you don't make an additional copy of it during garbage collection. So you can check the paper for how we handle that. We also have a lot of weird pointers into the middle of packed data structures. If we're talking about Java, you're used to an environment where you've got a graph of pointers, but they are polite enough to point to the beginning of the object instead of pointing right into the middle of your object at some unaligned byte offset, as we often do. We also collect these partially written objects. You'll be halfway through allocating a tree. Garbage collection is triggered. Now we need to relocate everything, including this kind of raw open end of the half-written object, which needs to continue allocating after you've collected. So those are some of the challenges that we address in the paper. Oh, little animation there. Here is the summary of the benchmark results you'll see in the paper. So we split our benchmarks here into two different qualitative sets. So one of them is these small allocation benchmarks. These are the ones where we expect to have a radically different performance with the GC-based version of Gibbon. And the other ones are kind of our traditional benchmark set of large traversals over data, where our goal is to just hold the line. If we can keep the benefits that Gibbon already has, we've done our job there. And we basically accomplished that, where we sped up by 3.39x on the small allocation benchmarks with our new techniques versus our old one, while holding the line on the other techniques, or on the large allocation benchmarks. Then, of course, we also compare against the Haskell compiler. We're still half as fast on small allocation benchmarks compared to GHC, which has been very well optimized over several decades for this kind of class of functional program that does many small allocations. In fact, Java doesn't do quite as well on those small allocation programs, so we're already on par with Java on the small allocation programs. OK, I mentioned those 3 challenges. I'm going to wrap up here, but I want to give you a little bit more detail on one of those 3 challenges. So how do we maintain sharing in the presence of these cramped and unaligned layouts? I mentioned that we don't have room for just unconditionally having a forwarding pointer, so we had to come up with some slightly new techniques here. You could actually forget about the forwarding pointers. Forwarding pointers are destructive. They go kind of in place of the object that you're relocating. You could do everything inside metadata off on the side, but that gets really expensive really quickly, especially when you're trying to deal with billions of very small objects efficiently for these bulk data applications. So our solution is to basically optimistically stick a forwarding pointer wherever we have room. If I see that your object is 9 bytes or more, then including that little header tag that's 1 byte, then I will go ahead and place a forwarding pointer. But during evacuation, if you land on something that is too small to have a forwarding pointer, we have some additional logic that allows you to scan to the right. And then we need to maintain a global invariant in the system, which is that if you land somewhere in the heap and you look for your forwarding pointer, you will be able to find something to the right that will enable you to figure out where you need to forward to. Here's a particular example of that, just to make it concrete. So we are relocating these dense objects into the old generation. We go ahead and we copy over some data. When we have the space, we're going to overwrite our data with the forwarding pointer. And when we don't, we're going to use this scanning logic. So we finish that initial evacuation. But now there's this other region over here that we haven't evacuated yet. So when we come along to evacuate this region, we want to copy that initial tag. But then we want to follow the indirection. Now, of course, we don't want to copy indirections willy-nilly. Our goal is to get rid of those, not to maintain them in the old generation. Right? So we want to instead kind of inline the data and keep following the indirection, subject to maintaining any sharing in the heap, because we don't want to duplicate data. So when we get over here, we need to do a little math. We need to figure out, OK, well, this is actually pointing to a byte that is not itself a forwarding pointer. But if I scan to the right, I can find the forwarding pointer, and then I can do a little math to figure out the address of the thing I actually want to point to. And then I could write an indirection over here to byte number 601 after doing that math. So you can check the paper for the full algorithm and the details there. But the end result is that you eliminate, we have a theorem that the number of indirections post-garbage collection is the minimum that you need to maintain the sharing in the original heap with no additional indirections beyond that. OK, so that is it. Our future work in this area is basically this is our first step into memory management for this system. We've introduced this copying collector in our young generation. And we have a lot more work to do to improve our collection in the old generation and so on. I'll leave this up while you ask any questions if we have a minute.
Thank you, Ryan. Great talk. We have a couple of minutes for questions.
Can you explain how you identify if something is a forwarding pointer or not? Does it depend on memory alignment, or how do you find out?
Yeah, so we've got this basic scheme here with any of these data types where there's the tag that represents which kind of object it is, and we're switching on that tag. And we just allocate special tags for these things. So we have a special tag that we use for indirection, and we have a special tag that we use for forwarding, and we have a special tag that marks this byte has been copied, but it's not big enough to have a forwarding pointer. So when we're going through and evacuating, we have a switch statement over these tags, and there's just one case that handles this and one case that handles this. The tag is always 1 byte in our current implementation. So we only have 256 of them. Yeah. But of course, you could always use a variable width encoding for that if you wanted to support data types with more than 256 variants, which do pop up a fair amount in practice, especially in automatically generated code.
Any more pressing questions? Oh, Tomorrow.
For the topic of Kulkarni, what if the old
Sorry. So what if there's not enough room to maintain the forwarding pointer? Where exactly?
Yeah. So in this case, there are.
There's sort of a forwarding. There's room for the forwarding pointer right after it. So I think you're going to kind of the worst case scenario, which is imagine that we've got a series of heap objects that are all 1 byte. It's like you never bothered to have a scalar. You only have a tree that is consists only of the structure of the tree, for example. You could have megabytes and megabytes of only 1 byte objects. So in that scenario, we do have some kind of fallbacks where we go to this side metadata table. But keep in mind, though, I will mention that if you're looking at a chunk of sub-word sized objects and none of them are yet forwarded, you can actually, in some cases, insert a forwarding pointer if you know that there are not any incoming pointers that are subdividing that particular span of 9 bytes. So there's a lot of kind of corner cases to get into there. But we just don't expect we hit that situation very often. Because there's usually kind of enough space, often enough, in any realistic data that you can fit in at least some forwarding pointers and just put most of the load on those forwarding pointers rather than on the side metadata that we have to fall back to. But good question. Thank you.